This is problem number 1 with Thomas, Gabe, and Marilyn. The initial question is, when heated, hydrogen sulfide gas decomposes according to that equation given. A 3.40 gram sample of H2S is introduced to an evacuated rigid 1.25 liter container. The sealed container is heated to 483 degrees Kelvin and 3.72 times 10 to the negative second moles of S2 at equilibrium. So problem number letter A says, write the equilibrium expression
Okay,
for
so
Kc.
Okay, so find the equilibrium expression Kc. You said Kc equal to the products, or the gaseous products, aqueous or gas products, so the concentration of H2 raised to the power of their coefficient, so it's 2, times the other one, since it has no coefficient, it has no power, over the reactants, which is H2S squared. And so that's Kc.
So Kc is equal to the concentration of the products over the concentration of the reactants raised to the power of their coefficient.
Amazing. Can you switch on? Why is this recording sideways?
So for part
B.
B, we are solving for the equilibrium concentration of the following gases.
Why is this recording sideways?
To do that, we
I'm
will
wondering.
set up our ice table. We are given, to start off, we need to find the molarity of H2S and the moles of S2. Of H2, I mean.
Yes.
So we'll do this part first. We start off with 3.40 grams of H2S times the mole of H2S over the molar mass, 34.02 grams. And to get molarity, we need to do it over liters, so 1 over 1.25 liters, which is what we're starting off with. So then we cancel out our units, grams cancel out, we're left with molarity, which is moles over liters. So we have 0.0800 molarity, or moles over liters, of H2S. So we plug that into here. Molarity of H2S. And we assume 0 for the products. And then going back to H2, we do 3.72 times 10 to the negative second moles of H2. And this is 1.25 liters to get molarity. So this gives us 0.0298 molarity, or moles over liters, of H2. And that is what we would use right here. Since we cannot go negative, it's obviously addition of 0.0298 molarity of S2, and that plugs in here as well because that's what we solved for. But since it has a coefficient of 2, we multiply by 2, which gives us 0.0595 molarity of H2. And this has to be subtraction since the products was addition. Again, a coefficient of 2, we multiply this times 2, which gives us the same number, 0.0595 molarity of H2 S. So, carrying our addition, this gives us subtraction here, 0.205 of equilibrium. This gives us 0.0595 at equilibrium of H2 and 0.0298 equilibrium of S2. So to go back, solving for
H2.
C, for
H2B.
part B asks for H2. The concentration of H2 at equilibrium is equal to this number right here, 0.0595. This is part 1. Part 2 is asking for the equilibrium concentration of H2S. So equilibrium concentration of H2S is equal to this number right here, 0.0205. And that solves for B.
Number C.
So C, calculating the Kc,
At 483 Kelvin.
so this is C. We would simply plug in our values. So we know that from part A, Kc is equal to this equation. So we simply plug in our values, which gives us this as our equation.
The equilibrium constant is the product of the equilibrium constant for the individual steps. So
Just using these three values given here, we plug them in here, and this gives us 0.251 as our Kc. So, part D asks for the partial pressure, and the container is at 483 Kelvin. We use the equation of PV equals nRT,
Uncharted territory.
and we are solving for P, so P equals nRT divided by V. This means that we use our initial moles of 3.72 times 10 to the negative second, which was given us to start. Our R is always going to be 0.0821. And our 483 Kelvin, which was told that we were at, divided by our volume of 1.25 liters. We cancel out our units. Moles cancel out, Kelvin cancels out, and liters cancel out. This leaves us with pressure equaling 1.18 atm.
Okay, part E. I shall be taking after this part. Okay, so part E is, we're given this equation at 483 Kelvin, so it's the same Kelvin, and you have to calculate the Kc. So, since this is 1/2 of the previous reaction given, you need to raise, where is it? Well, the answer we just previously got, wherever that is, to, it's point,
It's over.
okay, well, it's
Under here.
It's 0.251. Okay, that's the answer we previously got.
The equilibrium.
That's the equilibrium. And so we take that to the 1/2 power. We do not divide that by half. This is what a lot of people do. You do not want to do this. You end up getting 0.500, which is the answer. Okay.
And our 0.251 came from our equilibrium constant, which was that up here.
Right there. That's
That is it. Bye.